Lesson 33, finding the probability of independent and dependent events. So let's go through the different kinds of events. Independent events is just the outcome of the first event that does not affect the second event. And so this would be an example of you roll a number cube and you spin a spinner. What you get on the number cube does not affect what you get on the spinner. So those would be independent events. They have nothing to do with each other. So to calculate the probability, you take the probability of event A and you multiply it by the probability of event B. Dependent events would be the outcome of the first event does affect the second event. And so you have the formula, the probability of event A times the probability of event B, where probability of B is calculated under new conditions. So an example of this would be you are picking, let's say you pick a name out of a hat. You had a certain number of names in the hat. When you pick the first name, you had a certain probability of winning that time. But when you pick a second time, you don't replace that name. So you have fewer amounts of names in the hat when you pick it a second time. That means the probability of getting your name picked this time for whoever's left is better chance than it was before because we changed the amount. So that's a dependent event. So let's take a look at an example. What is the probability of spinning a 5 and landing on heads? These are independent events because what you get on one does not affect the other one. So the probability of spinning a 5. Well, there's 1 5 out of 5 categories on the spinner. So that's 1/5 chance. And landing on heads, there's 1 head out of 2 sides of a coin. So the probability of spinning a 5 and landing on heads would be 1 out of 10. So I just use the formula, probability of A times probability of B to get our answer. Next one, here we want to identify the events as independent or dependent. So rolling a 6 on one number cube and a 4 on another number cube. This would be independent, and the reason this is independent is because whatever you roll on one cube doesn't affect what you're rolling on the other cube. You still have the 6 options. Rolling a 6 on a number cube and then a 4 on the same number cube. So they're saying you're rolling them twice. So the first time you roll a 6, and then the second time you roll it, you get a 4. This is still independent because each time you roll it, you have 6 sides of a number cube, and you have an equal chance of getting each number. Drawing a red marble from a bag, keeping it out of the bag, and then drawing a blue marble, this would be dependent. And the key part would be you kept it out of the bag. So if you're keeping it out, if you pick one out and you never replace it, then it's dependent because the second time you pick it, the chances change. Drawing a red marble from a bag, putting it back in the bag, and then drawing a blue marble, that's independent just because you're putting it back in. So the chances are the same as the first time you picked it. Next one, tossing 2 coins, a dime and a quarter. It doesn't matter what you get on one coin because both coins have a heads and a tails. So the chances are even, so it stays as independent. Tossing the same coin twice, that's the same as the first one. You still get, it's an independent event. What you get on the first coin does not mean, or the first flip does not change the probability of getting a head on the second one. Putting 10 students' names in a bag, drawing 2 names without replacement. That would be dependent. So if you pick a name out, don't replace it and then pick another name out, you do change the probability. Putting 10 students' names in a bag and drawing 1 name per week to choose a room monitor, a student can be chosen more than once. This would be independent, and the reason is because A student can be chosen more than once, which means they're putting that name back in. And so the probability stays the same. It doesn't get affected. Next one, a card is chosen from a deck of cards, replaced, and then second card is chosen. Keyword is replaced. So the chances stays the same, so it's independent. A marble is drawn from a bag, kept, and then a second marble is drawn. Keyword kept tells you that the probability does change from the first drawing to the second, so this would be dependent. A coin is flipped and a number cube is rolled. Two separate items has no effect on each other, independent. Spinner is spun and the result is recorded, then the spinner is spun a second time. Same spinner, same probability, two independent events, they do not affect the other. Now let's look at using a tree diagram to identify the probability. I'm also going to show you can do it as a chart as well to save some space if need be. So a tree diagram shows the sample space for the events. What is the probability of the coin landing on heads both times, and heads and then tails? So here on the left-hand side you see a tree diagram. The first flip you get either heads or tails. The second flip you either get heads or tails as well. So let's just say the first flip you got heads. The second flip you can either get heads or you can get tails. But if you got tails the first time, your second flip you can either get heads or you can get tails. And so if you put them all together, you got heads, heads, that's here, or you get heads, tails, that's right here, or you get tails, heads, which is here, or you get tails, tails, which is here. So you have four different options. And we want to know what is the probability of landing on heads both times. So how many 2H's do we have? We only have one out of the four, so there's 1 out of 4 chances. What is the probability of getting heads and then tails? Now, the only one that we have heads and then tails is that one, so that would be 1 out of 4 chances. If you were to do this in a table, you would just put your choices at the top right here, and then this would be like your second flip. So if you got your first flip heads, your second one heads, or the first one, well, this is our first, this is our second. So we would say this, you get tails and then heads. It switched. It'd be, yeah, tails and then heads. Over here, you would have heads and then tails, and then you'd have tails, tails. So the same options there as you do over here. So you can see, okay, the first, how many double H's do we have? There's 1 out of 4. How many heads then tails? Still 1 out of 4. So let's do this one. A coin is flipped and a 6-sided number cube is tossed. Make a tree diagram showing all possible outcomes. What is the probability of landing on tails and on an even number? For the tree diagram, we're just going to do a chart because I think that will make it, we can fit that a little bit easier. So if they ever ask you for a tree diagram, I'll give you the option to do the diagram as well. So we have a coin that's being flipped. So you have two options. You can get heads or you get tails. And on a 6-sided number cube, you can get 6 different numbers. So we'll draw some boxes here. So this will be a 1, this is 2, this is 3, 4, 5, 6. So let's just fill it in. You could land on heads, but get a 1, a heads a 2, a heads a 3, heads a 4, heads 5, or heads and spin a 6. Or you can get tails and roll a 1. Tails get roll a 2, tails and a 3, tails and a 4, tails and a 5, or tails and a 6. So we want to know what is the probability of landing on tails and an even number. What I'm going to do is go to my chart and I'm going to circle all the ones that have tails and an even number. So tails and 2, tails and 4, tails and 6. So that is 3. And I have 2, 4, 6, 8, 10, 12 possible outcomes. Reduced would be 1 out of 4 chances. So you have 1 out of 4 chances of landing on tails and spinning an even number. Probability of dependent events. So these are where the first outcome affects the second outcome. So Natalia has 2 squares and 3 circles in a bag. Find the probability of drawing a circle, keeping it out, and then drawing another circle without the use of a tree diagram. So here we take the probability of A times the probability of B. So the probability of A, drawing a circle. Well, there are 3 circles in the bag out of how many total shapes? I have 2 plus 3, which is 5. So 3 out of the 5 are circles. So you draw a circle, you keep it. So now I only have 4 shapes in there, and you want to draw another circle. Well, I had 3 to start with. I took 1 out, so now I only have 2 circles left. So 3 times 2 is 6, 5 times 4 is 20. I can reduce this by 2 halves, and I get 3/10. So you have 3/10 of a chance of getting 2 circles in a row with keeping the first circle. Next one, find the probability of drawing a square, keeping it, and then drawing a circle. So again, probability of A would be drawing a square. So I have 2 squares out of the 5. You keep it. So now you only have 4 shapes in there. And now you draw a circle. Well, there were 3 circles in the bag, so you still have 3 circles in the bag. 2 times 3 is 6. 5 times 4 is 20. Reduce this by 2 halves, and you get 3/10. So you would have a probability of 3/10 for that example. Next one. A bag contains 4 red blocks and 3 blue blocks. Find the probability of drawing a red block, keeping it, and then drawing another red block. So we have a total of 7 blocks, and you draw a red one, so that's 4 out of 7. You keep it, so you have 7, or not 7, you have 6 left. And you draw another red block. So you start with 4, you took 1 out, didn't put it back in. So now you have 3 left. 4 times 3 is 12, 7 times 6 is 42. We can divide this by 3/3. 12 divided by 3 is 4. 42 divided by 3 would be 14. I can divide this by 2 again. This will give us 2/7. So our answer would be 2/7. Next one, find the probability of drawing a blue block. So 3 out of 7. Keeping it, so I only have 6 left over, and drawing a red block, which will give me 4 red blocks. Do the multiplication. I'm going to simplify first. I can divide a 3 here, divide a 3 here. Then I can divide a 2 here, divide a 2 here, end up with 2/7 again. And calculating odds. Odds, remember, is the expression of the likelihood of an event. So odds of something happening versus odds of something not happening. So you got to make sure you're careful on what they're asking for the odds are. So here, what are the odds of drawing a red? So really they're asking red versus not red. So the odds of getting a red, there are 6 red marbles, and there are 3 that are not red. And I need to simplify that so I can divide each number by 3, and I get 2 to 1. So you have 2 to 1 odds of drawing a red marble. What are the odds against drawing a blue marble? So not blue versus getting blue. So not blue, there are 8 that are not blue, and there's 1 that is blue. That is already reduced, so you have 8 to 1 odds against drawing a blue marble. Next one. A box contains 3 pink, 4 yellow, and 5 blue highlighters. Right, 1 highlighter is chosen at random. What are the odds of choosing a yellow? So yellow versus not yellow. So yellow, there are 4. Not yellow, there are 8. Divide each side by 4. You get a 1 to 2 chances of odds of choosing a yellow highlighter. What are the odds against choosing a blue? So no blue versus blue. So no blue is 7. Blue is 5. So you have a 7 to 5 chance against choosing a blue. And the next one, working with the spinner. Here we have 3 different colors on our spinner. What are the odds of spinning a black? So black versus not black. So black, we have 2 black segments, and we have 6 that are not black. So that would divide each side by 2. You would get 1 to 3 chances, 1 to 3 odds of spinning black. And what are the odds against spinning gray? So no gray versus gray. So no gray, we got 2, 4, 5. 5 that are not gray. We have 3 that are gray. So you have 5 to 3 chance or odds against getting gray. And a few more problems. Multi-step probability problems. Isaac has 6 blue and 4 white shirts in his closet. There are also 2 pairs of navy and 3 pairs of khaki pants in his closet. What is the probability of getting khaki pants and a white shirt? So how many khaki pants are there? There are 3 pairs of khaki pants out of 5 pairs of pants. And then he has a white shirt, 4 out of 10 shirts that are white. So find the probability. This would be 12 over 50. And divide by 2 halves. This would give us 6 out of 25 chances for the probability of picking khaki pants and a white shirt at random. Assume the pants and shirt are worn and put in a hamper. What is the probability of getting khaki pants and a white shirt the next day? So you have 1 less shirt. So now you only have 4 shirts. One of them, or 4 pairs of pants now. One of them was a khaki that you wore. So now you only have 2 khaki pants out of the 4. And then the shirts, you only have 9 shirts left over. 4 of them were white, but you wore 1, so now you only have 3 left over. So I can simplify this. This would be 6 over 36. Divide by 6, which would be 1 over 6. So you have 1 out of 6 chances of picking khaki pants and a white shirt the second day. Next one, the computer club has 10 boys and 12 girls. The chess club has 15 boys and 5 girls. Each club will choose a member at random to be club treasurer. What is the probability that both treasurers will be girls? So if you choose for the computer club, You have 12 girls out of the total of 22 students. Probability for the chess club, you got 5 girls out of 15 out of 20 students. We want to find the probability of both of those. So we're going to do some simplifying first. I can divide a 5 here and get 1, and divide a 5 here and get 4. I can divide a 2 here and get 6, divide a 2 here and get 11. So if I multiply straight across, I get 6 over 44. But I can divide this by 2 halves, and I get 3 over 22. So you have 3 out of 22 chances of that happening, that both treasurers will be girls. If both girls resign and a different pair of students is chosen, what is the probability that both treasurers will be girls again? So now you have 21 students in the computer club. Only 11 of them are girls. And in the chess club, instead of 20, since 1 resigned, you will only have 19 students left. 4 of them were girls. So you have 44 over 21 times 19 gives you 399. I cannot reduce that, so that would be your chances of both treasurers being girls again. And our last question, campers select 1 inside activity and 1 outside activity daily. There are 5 inside activities and 8 outside activities. What is the probability of choosing pottery and horseback riding on the first day? Pottery would be the inside activity. So the inside activity, you have 1 out of 5 chances of picking pottery, and you have 1 out of 8 chances of picking the horseback. That would give you 1 out of 40 chances of choosing a pottery and horseback riding on the first day. Inside activities can be repeated, but outside activities cannot be repeated. What is the probability of choosing pottery and swimming on the second day? So it's still 1 out of 5 chances for pottery. And picking swimming, that would be 1 out of 7 because you can't reuse the horseback riding, so there's 1 less. That would give us a probability of 1 out of 35 chances. So that is our lesson on independent and dependent working with probability.